This conference will now be recorded.
Hello everyone. The topic physical properties of alcohols. First 2 points we have covered in last class. Now we will see the other 2 points. Among isomeric alcohols, primary alcohols have higher boiling point, that is 1 degree alcohols, and tertiary alcohols lower boiling point. But that is true only when you have some isomeric alcohol. Isomeric alcohol means same number of carbon, hydrogen and oxygen will be there. So for example, if we have this linear chain 4 carbon alcohol, total number of carbon 4. Now this is 1 degree alcohol because the carbon with which OH is attached, that carbon is attached to only one carbon, this one. Now if keeping the carbon number same, if I draw the isomer which is tertiary, now it will be like this, that is Me3COH. Now here the carbon with which OH is attached, that carbon is attached to 3 more carbons, so that is why it is 3 degree. So this is 1 degree, this is 3 degree, and among these two primary alcohols that we have higher boiling point. Okay. So when it becomes tertiary, what happens? It becomes more spherical in nature, and so when it is more spherical, the surface area decreases, right? So that is why when surface area decreases, van der Waals interaction that is also decreasing. That means to reach the boiling point, that is for conversion of liquid to vapor state, we don't have to provide much energy. So that is why for tertiary alcohols, boiling point comparatively lower. That is, if we compare with 1 degree, it is lower. They have higher boiling point than the corresponding other organic compounds such as alkane, aldehydes, ethers, etc. because of intermolecular hydrogen bonding. So here they means alcohols. If you compare alcohols, its boiling point with alkane molecules, aldehyde molecules, ether molecules, then compared to all these other category of molecules, alcohols will be having higher boiling point. And the reason is here intermolecular hydrogen bonding is present. Here we have this picture where these green dotted line that are actually hydrogen bond. This molecule is CH3 then OH, that means it is methanol. This is another methanol molecule. Okay, then we have number 3 methanol molecule, and this is number 4. So there is hydrogen bonding between oxygen of one alcohol with hydrogen of another alcohol. And which hydrogen? That hydrogen which is attached to electronegative atom, oxygen. So because of this hydrogen type of hydrogen bonding, that is not present in case of alkane, because in alkane there is only carbon and hydrogen. In aldehydes also hydrogen bonding, that is aldehyde structure, if we write, it is like this. Okay, now hydrogen directly attached to any electronegative atom, that type of hydrogen here not present. So in case of alcohol, the hydrogen bonding that you can expect, that is not possible in this case. And in ether also, if we write the structure, suppose we have the simplest ether CH3 OCH3. Here also you have carbon oxygen carbon bond, but you do not have oxygen and hydrogen bond. But hydrogen must be attached to some electronegative atom if we have, if there is proper hydrogen bonding. So that is why when molar masses are very close, suppose you have taken one alkane molecule, one aldehyde, one ether, and one alcohol, keeping their molar masses very close to each other. Because why we are keeping it fixed? Because when molar mass is high, that is on this factor also boiling point is dependent. So that is why keeping this molar mass constant, if you are changing the type of molecule, not exactly constant, that is, it must be close to each other. If you are changing the category of molecule, alcohol to alkane or aldehyde ethers, then among these maximum boiling point you can expect for alcohol, and that is because of this type of hydrogen bond. Now after finishing physical properties, next we have to see chemical properties of alcohols. Now alcohols, as here we have this type of structure. Now chemical properties, that is actually because of two reasons. One is because of when carbon oxygen bond is broken, then you can expect one type of reaction, and when OH bond is broken, then there is another type of chemical properties. Alcohols exhibit wide range of spontaneous chemical reaction because of cleavage of either CO bond, this one, or OH bond. Now when the bond between carbon and oxygen is broken, that means now you will have R and HO minus. So when it is broken, they can act as electrophile because now there will be positive charge over R. So that is why now it is electron deficient and it will behave as electrophile. And in this case, some nucleophile can attack this electrophile, which is basically this R plus. But when OH bond is broken, now what you will be getting? You will be getting RO minus. That means now it will behave as nucleophile. So depending on that, whether it is cleavage of CO bond or OH bond, we can have two different types of reactions. The first category of reactions that we are going to discuss, which is reactions involving cleavage of carbon oxygen bond. So this is A, and B will be the other possibility, which is cleavage of OH. So under this heading, reaction where CO bond is broken, one by one we will see the reactions. Reaction with hydrogen halides, fine, that is in general you can write the formula HX. Now same type of reaction is also possible with thionyl chloride, PCl3, PCl5, but here mainly we have written reaction with hydrogen halide, that is HX. Alkyl halide formation from an alcohol. Now this reaction you can consider, that is this is the reaction general form, as if it is preparation method of alkyl halide starting from alcohol. So from the point of view of Rx, it is synthesis of Rx, alkyl halide, and if you consider from the point of view of alcohol, then it is chemical properties of alcohols. So alcohol, when you are treating it with HX, you are getting Rx, fine. Alkyl halide formation from an alcohol and hydrogen halide, that means HX, affords an important example of a reaction where carbon oxygen bond of the alcohol is broken. So carbon oxygen bond, that is this bond is broken, and this type of reaction it undergoes the mechanism nucleophilic substitution, SN1, SN2, two different types of mechanism possible, but here carbon oxygen bond is broken, right? So that is why we are discussing it under this heading, reaction involving cleavage of CO bond. The mechanism of this displacement, it may be any of these two, and that depends on what type of structure of alcohol we have taken. Now ROH, this is actually general expression, but suppose you have taken HBr. So here RO bond will be broken and OH will be replaced by Br minus. Finally we are getting RBr. Now if we consider this mechanism, first what is happening, HBr or HX, whatever you say, this hydrogen is acidic. So in presence of this hydrogen, first this oxygen can be protonated and now oxygen is positively charged. Now this RO bond when broken, that means carbon oxygen bond broken. So OH2, it is a very good leaving group. So see, water molecule is removed and you are getting R plus, which is the electrophile. Now Br minus is attacking here. So this is the mechanism that you can observe in SN1, and if it is SN2, then though detailed discussion we have done in the other chapter, which is haloalkane and haloalkane, fine, you can find the details there, that is details of SN1 SN2 mechanism. If it is SN2 mechanism, it is single step reaction, and here directly, that is the RO bond cleavage and BRR bond formation, that is carbon Br bond formation, both are taking place simultaneously. So that is why Br minus is attacking R from the back side and from the other side OH2 is removed. Okay, but whatever is the mechanism, final product is alkyl halide. This is number one example under cleavage of CO bond, and we have seen this example with HX. But now we will see some other reagents that also you can use. Thionyl chloride, very important reagent, which is used for the same purpose, and it is SOCl2. It is also useful for the preparation of alkyl chloride, especially when the use of strongly acidic reagents is undesirable. So strongly acidic reagents undesirable means you cannot use HX, because HX, it is acidic, HCl or HBr, HI, whatever it is acidic. But suppose the molecule that you have taken, it is acid sensitive. So in that case, you cannot use HX. But still you want to make alkyl halide. So what you will do? Then you will take SOCl2. Here we can see the mechanism. First, the lone pair of oxygen, it is attacking this sulfur. Sulfur chlorine bond is broken. HCl is removed. That is, this H and this Cl together, HCl is removed, and we are getting oxygen sulfur bond. So first we are getting alkyl chlorosulfite, RO, SOCl, and finally SO2 will be removed. And what we are getting? We are getting RCl and SO2. So here byproducts are, in the first step HCl is removed and SO2 is produced in the second step. So final, that is net reaction, if you write, it will be ROH plus SOCl2 equal to RCl plus HCl plus SO2. Addition of 1 mole of an alcohol to 1 mole of SOCl2, it gives an unstable alkyl chlorosulfide. So the first intermediate that is produced, that is not very stable. So finally it will be decomposed if you are heating it mildly to yield the alkyl chloride and SO2. Here that is, you can also consider it as if it is breaking of this RO bond, that is form alkyl chlorosulfide if you consider the mechanism. So this RO bond is broken, SO double bond is there, and HCl bond will also be broken. Okay, or you can also consider it as if this RO bond is broken first, there is negative charge over oxygen, because there is double bond between oxygen and sulfur, but one of these bond will be broken. So now that is why there is negative charge over oxygen. Finally SO2 is removed and Cl minus is there. So in both these ways you can consider the mechanism, but final product is alkyl halide. You can also use some other halides that are useful in converting alcohols to alkyl halides, but there is the same type of reaction you can also do with these phosphorus halide reagents. It may be PCl3, PBr3, PI3 and PCl5. So in this box you can see all the different methods starting from alcohol. First reagent we are using HCl in presence of anhydrous ZnCl2, which is Lucas reagent. This test is also used to determine whether alcohol is 1 degree, 2 degree or 3 degree, and it is also known as Group's process. This reagent combination is known as Lucas reagent. Fine. Anhydrous ZnCl2, this type acting as catalyst, but you need catalyst only when alcohol is 2 degree or 1 degree, because if it is 3 degree, HCl is enough. It is more reactive. Then in presence of NABr and H2O, in situ there will be formation of HBr, and this HBr is actual reagent. So HBr will react with alcohol, you will be getting RBr. Then reaction with PX3, where X may be Cl, Br or I, and when it is PX5, it is only PCl5, not PBr5 or PI5. These molecules are not used, okay, and actually they do not exist. And lastly we are using SOCl2, and whenever there is use of SOCl2, pyridine is also used. Now the reason is why it is used, because here byproduct is HCl, and pyridine, it will consume this HCl, because pyridine is basic in nature. So base will react with acid. Now if HCl is consumed, and according to Lee-Chatelier principle, equilibrium will be shifted towards right hand side, because the concentration of one of the byproduct is decreasing as it is reacting with pyridine. So more RCl will be produced from ROH. That is the purpose of using pyridine. This process is also known as Diagen's procedure. Okay. So three types of reagents we have used for formation of alkyl halide. One is HX. Now sometimes HX is directly used, or you can use this type of mixture where in situ HBr is produced or HCl is produced. Okay. So this Na basically replaced by this H and you are getting HBr. Then the next reagent we have seen SOCl2, and you also have to use pyridine along with it. And the third type is phosphorus reagents, that is phosphorus halogen reagents. So these are the reagents that we can use for these chemical properties of alcohol, which is formation of alkyl halide from alcohol. Here we have this reaction where you can see this is actually alcohol molecule and it is treated with HCl. We are getting the major product A. A you have to find. 4 options are given. What is the final product? There may be different types of product, but you have to focus on major product, not the other minor products. If we look at the options carefully, option 1 and option 4, these two products are basically substitution. Simply OH is replaced by Cl. Though you can say that the position of OH is this carbon. So this product that you can see in option 4, here direct OH is replaced by Cl, no rearrangement. But if you consider option 1, there is rearrangement, but common thing is that 1 and 4 both are substitution. There is no elimination, because whenever there is elimination means OH will be removed along with some hydrogen atom. So as if it is net removal of water. So when this type of elimination is occurring, CC double bond will be formed, right? So see, if you are removing this OH and one hydrogen from this methyl, you will be getting option 3 molecule. But if you are removing OH and this hydrogen from cyclohexane ring, now you will be getting option 2 molecule. So 2 and 3, these two are elimination. 1 and 4, these two are substitution. Okay. This is the starting substrate in presence of H plus, which is basically coming from HCl. First, there is protonation of this oxygen, and oxygen is now positively charged. It will be removed in the form of water. There is positive charge over carbon. Now this carbon is 2 degree. So you have to consider, that is, you have to check in the molecule whether there is any rearrangement possible or not. Because sometimes after rearrangement, you can get more stable carbocation. So that is the reason you have to check whether rearrangement possible or not. Here 1,2 hydrate shift is possible. And which hydrogen? This hydrogen, it will be shifted to this adjacent carbocation in the form of H minus. Hydrate shift means H minus. Hydrogen atom carrying negative charge. Now after this shift, you are getting the carbocation which is 3 degree. Now this is more stable compared to the previous carbocation. So this is the driving force for the formation of, for the rearrangement process, right? Once you are getting this positive charge, now Cl minus, which is basically generated from HCl, because H we have already used in the first. Cl minus is still there in the middle. So this Cl minus, it will act as nucleophile and it will attack. So it is actually SN1 mechanism. So you will be getting substitution product. So in the previous slide also, when we have discussed formation of alkyl halide starting from alcohol, what we have seen, 3 types of reagent you can use. You can use HX, SOCl2 or phosphorus halide. So this, in this question, as we are using HCl with alcohol, so obviously we will get substitution as the product, not elimination. So option 2 and 3 you can cancel out. But among 1 and 4, though both are substitution, now you have to cancel one option. And how you will do so? You have to check whether rearrangement possible or not. Because if you are not doing the rearrangement, suppose without rearrangement, directly you are considering this carbocation and you are adding HCl. So in this case, Cl will be attached to this carbon, and which molecule you will get? You will get option 4 molecule. But this is option 1. That is, if you are doing rearrangement, then substitution of option 1. But if you are not doing the rearrangement, directly you are doing the substitution, it will be option 4. But sorry, correct option is this one. After the first reaction, which is formation of alkyl halide by substitution starting from alcohol, the second reaction number 2 is dehydration. Now this is also under CO bond cleavage, right? So when it is dehydration, from the name you can understand it is removal of water molecule, that is minus H2. So OH will be removed along with some hydrogen atom. When alcohols are heated with a suitable dehydrating agent means the reagent we can absorb water, because ultimately water is removed from the alcohol molecule. So there must be some dehydrating reagent, right? The H and OH present in the adjacent carbon of alcohols, they will be lost. So OH is attached to some carbon, and which hydrogen atom? The hydrogen which is adjacent to it, that hydrogen will be removed. But finally what you will be getting? You will be getting some elimination reaction. So that is why CC double bond will be formed. Here we have taken ethyl alcohol molecule, very simple. Now H2SO4, when it is concentrated, it is having dehydrating property. First there will be protonation. After protonation, oxygen is positive now, and HSO4 minus is present in the medium. Now it will help to remove this H. So CH bond will be broken, and carbon oxygen bond is also broken. Remember, this reaction is under the heading cleavage of carbon oxygen bond. So carbon oxygen bond must be broken, that you can see here. Finally you are getting CC double. Now not always you have to use concentrated H2SO4, so that is the most common reagent, but some other reagents also you should consider and remember also, because in question you can also get these reagents. H3PO4 and sometimes anhydrous ZnCl2 or alumina Al2O3, these can also be used, but mostly concentrated H2SO4 used. Example we'll see. This is very simple example with ethyl alcohol, but now the example that you are going to see, there will be involvement of rearrangement also. So this is a molecule OH, that means it is alcohol, first in presence of H2SO4. This molecule is nothing but H2SO4. It is written in a different way so that it helps us to understand the mechanism. Otherwise it is H2SO4, nothing new. Oxygen, its lone pair is attached to this H, and oxygen is positively charged. Carbon oxygen bond is broken, water molecule removed. So this is a dehydration. You are getting a carbocation, but it is 2-degree carbocation. You have to check rearrangement possible or not. Yes, rearrangement is possible. If you are shifting this, any of these 3 methyl, suppose you are shifting this methyl, now new positive charge will be generated here, which is now 3-degree. So this type of rearrangement is possible because you are getting 3-degree from 2-degree. Now once you have obtained this 3-degree, next you have to remove one hydrogen atom. Now if you look at this molecule carefully, you have 2 methyl group in the right hand side, that is CHMe2 group right hand side, and in the left hand side you have 2 methyl group. Now these 2 methyl group, they are actually equivalent, so there may be removal of hydrogen from any of these 2 methyl group. So if this hydrogen is removed, you will be getting double bond in this position, but if the other hydrogen is removed, you will be getting the double bond in the right hand side. So this is beta hydrogen elimination. Why it is beta hydrogen? Because OH with, that is the carbocation, where it is attached, you have to consider this carbon as alpha carbon, because OH is attached to this carbon, though there is rearrangement. So I shouldn't say that, because OH is attached to this carbon. So you can also consider this carbon. Now with respect to this one, these 2 positions are beta. But now as after rearrangement you are getting this new carbocation, so you can consider as if this is beta hydrogen, these three are beta hydrogen, this is also beta hydrogen. So any of these two beta hydrogen can be removed, and depending on which one you are removing, if you are removing the left hand side beta hydrogen, that is A type of hydrogen, this will be the final product. But if you are removing the right hand side beta hydrogen, okay, that is if you are removing this one, now double bond will be generated in this position and this will be the molecule. So see here, 33% of this alkene is produced, 64% of this one is produced. And if without rearrangement, directly if you are removing this H plus, that is, remember the first carbocation before rearrangement. Now in this carbocation, you have two different types of beta hydrogen. So with respect to this carbocation, here this hydrogen is beta. Actually only one type of beta hydrogen is present, because the other beta carbon there is no hydrogen attached. So you can remove only this hydrogen. After this removal of this H, there is double bond formation. But see, it is very, very minor, 3% only, because it is expected. This carbocation, its lifetime is not very high, because once it is formed, there will be rearrangement, methyl shift, and you will be getting the more stable 3 degree. So the next H plus removal, that will be from 3 degree, not from 2 degree. So that is why its yield is so less. And when it is from 3 degree, that is a newly generated carbocation after rearrangement. Now also there are two possibilities, and see, this one is major because it is almost double the amount of the other one. So if this type of molecule is given and different options are there, and if it is asked which one is the major one, then this is the correct answer. Now why it is 3%, that we already know, but among these two, suppose this one and this one, if we consider, why this is major, because the double bond that is generated here and the double bond that is generated here, suppose it is A, it is B. So for B, the double bond is more substituted, and more substituted alkenes are always more stable. You can also count the number of alpha hydrogen. So these are the alpha carbon with respect to CC double bond. How many alpha hydrogens are there? 3 into 4 methyl, that means 3 into 4, 12. But if you look at the other one, that is A, you have 3 alpha hydrogen and 1 alpha hydrogen. So number of alpha hydrogen, that is very less. So if you have trouble to understand that is which one is more substituted or less substituted, obviously you can also do the counting the number of alpha hydrogen. So when number of alpha hydrogens are high, what happens? Alkene becomes more stable because hyperconjugation process is also high. But just simply looking at the structure without counting the alpha hydrogen also, you can decide which one is more substituted. So in this CC bond, you have total 4 substitution, right? But in the other one, you do not have any substitution in the left hand side. It is simply hydrogen. We are talking about alkyl group substitution, but you have substitution at these two positions. So that is why the alkene you are getting from right hand side B, that is major product. The major product B in the following sequence of reaction is: starting material is alkene, CC double bond is there. What reagent you are using? You are using B2H6, H2O2, HO minus. So this is hydroboration oxidation. Remember in the last class we have discussed it, which is basically the preparation method of alcohol. Suppose you want to make alcohol starting from alkene, and it will be anti-Markovnikov product. So in this CC double bond, there will be addition of H and OH. So final product after hydroboration and oxidation is alcohol. So A must be alcohol. Then you are using dilute H2SO4. So reaction of alcohol and dilute H2SO4. Finally, you are getting B. Now, if we look at the options, what kind of molecule will be B? That you can easily understand. See, option 2, 1, 2, 3, 4. In all cases, you have CC double bond. So what it means? It means there is removal of H and OH, that is net removal of water. So this is actually dehydration reaction. Though it is also true in the question, it is simply mentioned dilute H2SO4, and normally for dehydration we use concentrated H2SO4, right? But you don't have to worry here because all the options are basically CC double bond present. So it means what? Whatever is the option, it is always the dehydration, right? So you don't have to worry about whether it is dilute H2SO4 or concentrated, because whatever it is, product is always the dehydration product. But which one is the correct structure for the final product, which is B, that you have to find. So first you have to know the right structure of A. So A is alcohol, and remember in hydrocorrosion oxidation it is following anti-Markovnikov rule. Now if we look at the alkene molecule, that is the starting molecule that is given here. This is suppose number 1 carbon, this is number 2 carbon. Number 1 carbon, there are 2 alkyl group. Number 2 carbon, there is 1 hydrogen and 1 ethyl group, right? So that means among 1 and 2, which carbon is containing higher hydrogen? It is number 2 carbon. Okay, so according to anti-Markovnikov rule, if we follow, as 2 carbon, which is basically this one, 2 carbon is having more hydrogen attached, so OH will be added to this according to anti-Markovnikov rule. So this is the structure of A. Next we are using H2SO4, though it is dilute, but we will consider dehydration, because if we do not consider so, you cannot reach the alkene molecule, because all the options are alkene molecule. Water will be removed, because after protonation OH will be OH2 and OH2 will be removed. So there will be formation of carbocation. Now this carbocation is 2 degree, and if you are doing rearrangement, that is 1,2 hydride shift, sometimes you will see that there is a chance of hydride shift, sometimes there is a chance of methyl shift. So you have to that depends on the structure. There is no hard and fast rule. Your aim is to write after rearrangement the more stable carbocation. So if you are getting the more stable carbocation by H minus shift, that is okay. If you are getting a more stable carbocation by methyl shift, that is also okay. So whatever is the shift, here our main purpose is to get more stable carbocation from the less stable carbocation. So here we are getting 3 degree starting from 2 degree. So this newly generated carbocation is now 3 degree, because the carbon which is carrying positive charge, that is attached to 3 carbon. So this is the newly generated carbocation. Now in this carbocation, next you have to remove hydrogen atom, and that you can remove. See, there are total 3 positions. You can remove it from here. Suppose this is A. You can remove it from the right hand side, CH2, or you can also remove this hydrogen, which is C. So 3 possibilities are there, right? Now further methyl shift is also possible. If there is further methyl shift, that is if this H is also shifted to carbon, you are getting another 3 degree. Okay, so this rearrangement, even if you do not do, it is also okay, because without doing it also you can reach the correct structure. Now after this hydride shift, next there will be removal of H plus. Now this carbocation, if you consider, you can remove H plus from this 2 methyl, but in that case, what your double bond, CC double bond, that will be terminal, and that type of structure is not stable. You have to remove the H plus. This is actually removal of H plus. So here this H is actually removed, and that is why CC double bond formation is taking place in this position, right? But you can also get this product directly from this carbocation. And how you can get, if you are removing this hydrogen, that is by removing number C hydrogen also. Suppose I am writing here HC. So removing HC also, you can get the same product, and this is major product because it is more substituted product. Okay, that is what is more stable. See here, total 4 alkyl substituents are there, and this type of alkene is also known as ZJ. Normally we use this term ZJ for Hoffman in elimination reaction. So this will be the major product. that is it is matching with basically option 2. But suppose if you are removing a type of hydrogen, then the position of double bond, it will be like this: H2C double bond C, CH Me2, and this side CH2 CH2 CH3. So is it present in any of this option? Yes, it is present. It is actually option 1 molecule, but this is not major. And if you are removing B hydrogen, what alkene you will get? You will get the alkene H3C, then double bond CH, then ethyl group, and here CHME2. Now this is actually option 3 molecule, right? And option 4 molecule is basically if you are removing H, this H from this 2-degree carbocation, that you will be getting option 4. But obviously you have to do rearrangement because you can generate 3-degree from 2-degree. Then why you will remove H plus from 2-degree? So that is why this is not correct. Option 4 is not correct. And once you have obtained this 3-degree, there are 3 possibilities. So when you are removing A and B type of hydrogen, you are getting option 1, option 3. And when you are removing C hydrogen, you are getting the major product, because now you have the maximum substituted double bond. So why it is maximum substituted? Because if you compare with the other options, see in option 2, total 4 substituted. So I can also suggest one thing, that is a trick you can say. That suppose if you are in a hurry, you do not have so much time to write mechanism, then directly look at the options. In options, only option 2, it is maximum substituted, total 4 alkyl groups. But if you look at 1, there are 2 hydrogen, 2 alkyl group. Then option 3, 2 alkyl group, and other side 1 hydrogen, 1 alkyl. That means 3 alkyl group. And in the option 4, CC double bond, you have 1 H, 1 methyl, and the other side 1 H and this large alkyl. So here you have only 2 alkyl substituent. Here you have 3 substituent. Here also 3. Only in option 2 it is 4. So even without considering the mechanism, though I will always suggest that you should write the proper mechanism. But if you are lacking in time, write directly from the options, you can choose option 2 because this is the most substituted alkyl. The question is, when neopentyl alcohol, we have to write the structure of it. But read the question first. When it is heated with an acid, it slowly converted into 85-15 ratio mixture of alkene A and B. So A is major, B is 15%. It is mine. But you have to find both of these alkenes, A and B. So option 1, this is A and B respectively. So first A, then B. Here you can find this molecule A, that is, there are different types of A. So you can see these two are actually same. Option 1 and 4, both A are same. Similarly, if you consider B, these two B are same, and 3 and 4 also B are same. So different permutation combinations are there. But first we have to write the structure of neopentyl alcohol. Now neopentyl, it means what? Total number of carbon must be 5. Now it is very common mistake. We become very confused between tertiary butyl alcohol and neopentyl alcohol. Tertiary butyl group is Me3C. Tertiary butyl, that means tertiary carbon is there attached to 3 carbon, and butyl, that means 4 carbon. And then there is some group. It is not necessary OH. I am trying to represent in general. Suppose you have tertiary butyl amine, tertiary butyl alcohol, tertiary butyl any cyano compound. So this G may differ. It is, in our case, it is alcohol. But remember, when it is tertiary butyl substitute, 4 carbon, tertiary carbon must be present. But if it is neopentyl, now in this case also, There is some similarity in structure, but it is not same. Now it is Me3C, then another CH2, then the group. It may be amine, it may be OH, it may be cyano, whatever. But see, now total number of carbon is 5, and group, corresponding group is attached to 1 degree carbon. It is not 3 degree, but here it is 3 degree and total number of carbon is 4. So this is the difference between neopentyl alcohol and tertiary butyl alcohol. But now you can understand it for any structure, alcohol, amine, whatever. So neopentyl alcohol is this molecule, that is Me3 methyl group, then CH2, then OH. You are heating with acid, and in options there is CC double bond, so it must be some elimination. Now when you are using acid, OH will be protonated, so carbon oxygen bond will be cleaved. You will be getting some positive charge over this carbon, but this is 1 degree carbocation, so you must do rearrangement. Now after rearrangement, this is neopentyl alcohol, this is CH2 plus, methyl rearrangement possible. So one of the methyl group, now it will be shifted, you will be getting the positive charge. Now this is 3 degree. So from 1 degree, now you are getting 3 degree. So that is the driving force for rearrangement. Now once you have obtained 3 degree, you have 2 methyl group and both are symmetrical. If you are removing hydrogen from any of this methyl group, then the structure that you will be getting is this. So this is B. But if you are removing H, because these hydrogens are beta hydrogens, these 2 hydrogens are also beta. If you are removing that, you will be getting CC double bond here. And this is major because it is more substituted. See, in this case, you have total 3 alkyl substituted, but here you have only 2. That is why it is more substituted and more stable alkyl. So this is the structure of A. Now, if this is the structure of A, that you can find in both option 1 and option 4, but you also have to match B. Now B is matching only in case of option 4, not in option 1B. Okay, so that is why last one will be the correct option for A and B. Again, we have alcohol molecule. We are using dilute H2SO4, right? The major product of the following reaction we have to find. Now the product, the substrate that is given, there is CC double bond, right? Now when there is CC double bond, and in the options, option 1 and option 3, these two are cyclic structure, right? But if you consider option 2 and 4, they are open chain structure, and here as if this CC double bond, across this CC double bond, carbon H and OH is added. So see, if you consider option 2 as if it is attachment of H and OH, then in option 3 also it is attachment of H and OH, though their positions are reversed. And the other CC double bond, here also H and OH attached, H and OH attached. Okay, so this for these two options, it is as if addition of H and OH. But if you consider option 1 and 3, see, OH is still there, right? Now it is normal convention that whenever you have any cyclic compounds, they are actually more stable than the open chain structure, because their structures are more compact, and 6-membered structures are always more stable than the 5-member structure, right? So you can easily cancel what 2 and 4, it will be cyclic structure. Now both 1 and 3 are cyclic. Now among these two options, 1 and 3, here it is 5-membered, this is 6-membered, and here CC double bond is only 1 alkyl substituent, because these positions there are hydrogen. So this is terminal type of alkene. But if you consider the CC double bond in option 3, now you have total 3 alkyl group substituent, only 1 hydrogen. So obviously this will be more stable. So just based on this common sense, you can choose option 3 as the right option. Okay, but we'll also see the mechanism. The molecule alkene, actually there are two CC double bond. It is drawn here in the same orientation as you can see in the question. But when you will do protonation with this OH in presence of H2SO4, though it should be constant H2SO4, but question is it is made in this way. Okay, there is OH. First there will be protonation and carbon oxygen bond broken. So you are getting this type of 1 degree carbocation. Now, if the next stage there is this cyclic structure as you can see. But if you are having trouble to understand how you are getting this, and that is very common, it is really difficult to write directly from this type of linear chain open structure, and now you are writing the ring structure. So what you will do, you can do, write the same structure of carbocation, which is see, one, this is one carbon, then 2, 3, 4, 5, 6. So this is 1, this is 2, this is 3, 4, 5, 6. And at 6th position, there is double bond and 2 methyl group, right? Now another double bond is also there between 2 and 3. And at 3 position, there is methyl group also, right? Now when you have this type of structure, there is actually bond formation between carbon 1 and carbon 6. So let me write this carbon 1 in this way. Carbon number 2, CH2, and this plus. So what I am doing, I am bringing this carbon number 1 close to carbon number 6 so that the mechanism can be easily understood. Next, what will happen? The CC double bond, it will be attacking, that is a 6. If you consider the CC double bond as if it is accumulation of negative charge and positive charge, suppose like this. So as if the CH2 plus that is here, and I'm just connecting it in a simple way. So this negative charge as if it is attacking this CH2. So when it is attacking there, positive charge will be generated at this carbon, and this is basically this carbon number 7. So positive charge will be generated at carbon number 7, which is this structure basically. So see, this is carbon number 7. And finally, 1H, that is the next thing what you can do. 1H can be removed, but if you are doing so, you will be getting CC double bond. But in option 1 and 3, it is basically substitution, right? So as it is dilute H2SO4, water will be present in the medium. It is not concentrated. So this water, now it can attack here. So when it is attacking here, 1H will be removed. It is as if OH is added finally. So it is matching with which structure? It is matching with option 3. Okay. So first there is protonation, there is removal of OH2, but it is not net removal of H and OH, because as it is dilute H2SO4, finally in the last step there is again attack of water, and you are getting a new OH, because the first OH that you can see, that is actually not present. It is already removed in the form of water. So the final OH that you can see in the product, that is actually coming from water molecule. So this OH is not same as this one. Fine. So option 3 is the correct option. So all these two reactions basically, one is dehydration, another one is addition of HX, so that you can get alkyl halide from alcohol. These two are under the heading of when it is carbon oxygen bond cleavage. But the other possibility is type B. Now these reactions will be involving cleavage of oxygen hydrogen bond. The first type under this category, reaction with metals. Now we know that alcohols, as this H is attached to oxygen, it will have some acidic property, though it is far less acidic than water, but still because of this mild acidic property, they can react if you are having some active metals, that is sodium, potassium, aluminium, not just any metal, it must be active metal. And what you are getting, now H is replaced by sodium. Now two alcohols if you take and two sodium, there will be net removal of two hydrogen atom. So these two hydrogen atom together, it will make diatomic H2 molecule, and you will be getting sodium alkoxide. Now as it is general structure, because we do not know what is R group, so you will call it alkoxide, fine. But suppose if it is methyl, you will call it methoxide. If it is potassium, it is potassium methoxide, fine. If it is propyl group, it is sodium propoxide, like this. But alkoxide is the general term. Next type of reaction that is possible for OH bond cleavage is esterification. We know that when there is reaction between alcohol and carboxylic acid, or not just carboxylic acid, you can also take acid chloride, or you can take acid anhydride, and final molecule is ester. Phenol also can undergo the same type of reaction, though right now the discussion is limited to alcohols, because phenols will be discussed separately. It is aromatic, containing aromatic ring, so its properties are more or less different. Here we have taken this carboxylic acid and alcohol R prime OH, and in presence of acid catalyst we are getting ester. So here this bond is broken, and from the acid side this OH and this H, as if it is net removal of water. So see, this is the water molecule, and this carbon is now attached to this oxygen. So you are getting RCOOR prime. Now here we have taken a specific example, which is benzoic acid we are using, that is as carboxylic acid. And for alcohol, what we have taken ethyl alcohol. Here H which removed, and this carbon is attached to oxygen. So this is a newly generated bond, carbon oxygen. But here important point to remember, this bond is broken, cleavage of OH bond. Okay, one thing also, though it is already mentioned, if it is acid chloride, suppose you have taken any acid chloride RCOCl, and you have taken any alcohol, I am now writing it as R prime. So if you remove this, then also you can get ester. Or if you have taken some anhydride, general structure is RCOOCOR, and there will be alcohol. So as if here you are removing OCOR group and this H. So finally you will be getting RCOOR prime. So you can use carboxylic acid, acid chloride, or acid anhydride. Some more examples we will see for esterification. Here 3 carbon, then CO2H, that is butanoic acid, total 4 carbon, and ethyl alcohol we have taken. So here as if removal of this H and this OH and H, and the carbonyl carbon, it is now attached to this oxygen. So you are getting this type of ester. Then carboxylic acid with methyl alcohol acid, you are getting methyl benzoate. Now the next example is interesting, because here the acid group and OH both are part of the same molecule. So when you are removing this H and OH, there is bond formation between this oxygen and carbon. So whenever you have some open structure, you are generating some cyclic structure, I will always suggest put numbers. It will help you to write the structure. So this is 1 carbon, 2, 3, 4, 5, and the oxygen is 6, and 6 oxygen and 1 carbon is attached. So that is why it is 6, it is 1. So 1,6 bond is formed. So it will help you to write the cyclic structure. It is cyclic ester. Next structure is also OH and CO2H in the same molecule. Again you are getting cyclic ester, but now it is 5 member because one carbon is less. And the last example, here we have two CO2H group in the same molecule. So as if it is you have taken 2 carboxylic acid. So that is why the alcohol that you are taking, that also you have to take 2 equivalent. So as if it is 1:2. Normally it is 1:1 reaction. But as you have 2 carboxylic acid in the same molecule, now it will be 1:2 reaction. And both side there is esterification. Alcohols can also react with acid chloride, as I have mentioned there. You can also see it here. Acid anhydride we have taken. So OCOR, sorry, it's not OH. This H and OCOR, these two will be removed. You will be getting ester. This is byproduct. And if it is RCOCl, then Cl is removed, H is removed. You are getting RCOOR. Okay. So this can also be used instead of taking carboxylic acid. Oxidation, the third type of reaction. Now alcohol, when it is oxidized, basically oxidation of alcohols, there is formation of C double bond O. Now OH is there, alcohol, and now I will not write the structure as ROH because here as if there is net removal of 2H. So I will write the structure like this, and there are 2 more bonds attached with carbon. So as if it is removal of 2H atoms. So finally what you will be getting, there will be generation of CO double bond and 2 more groups. So there is a formation of C double bond O with cleavage of OH bond. This is OH bond cleavage and also CH bond cleavage. This CH bond. You can also call this dehydrogenation because as if you are removing 2 hydrogen. Remember, when we add hydrogen, it is hydrogenation. But when we remove hydrogen, it is dehydrogenation, and it is involving loss of H2 from alcohol. When it is 1 degree alcohol, there is oxidation. You are removing these 2H. There will be double bond between carbon oxygen. But if the oxidizing agent is very strong, further oxidation will be there, and ultimately RCOH aldehyde that will be converted to carboxylic acid. So primary alcohol is oxidized to an aldehyde, which in turn is oxidized again to carboxylic acid. Now the second step is not possible if it is mild oxidizing agent. It will be stopped here. But if it is very strong, further oxidation to carboxylic acid will be there. So strong oxidizing agent, if you have taken potassium permanganate, you will be getting obviously carboxylic acid. But if you are using CrO3 in anhydrous medium, that is chromium oxide, pyridinium chlorochromate, DMP, then Swan reagent, if these are used, then there will be, you can isolate aldehyde. So PCC is pyridinium chlorochromate, PDC is another reagent, pyridinium dichromate. In Swan reaction, Swan is actually not reagent, it is actually Swan oxidation we call it, where these reagent combinations are taken. Details you don't need, just remember when it is Swan oxidation of alcohols, you will be ending at aldehyde, not carboxylic acid. And DMP is desmarting. We have also the structure of this. This is DMP, desmarting, this is PCC, and this is PDC. So when you are using this type of reagent, you can stop the reaction in aldehyde, but if it is K-manophore, which is very strong, then you will get carboxylic acid. Some more information we will also see regarding oxidation, but today we will end here. Thank you for listening.